everybody, welcome to lesson 5.4. We're talking about the work-energy theorem. This theorem is profound because it connects the weird concept of work with the important concept of energy. This is something useful in engineering when you're talking about making efficient cars, efficient power plants, two of the most important things that we are working on today. It's important because it tells us how we can change the energy of certain objects. But without further ado, let's write down the theorem. The theorem is quite subtle, and it states that when a net external force does work on an object, when a net external force does work on an object, the work done is equivalent to the change in the object's kinetic energy. When a net external force does work on an object, the work done is equivalent to the change in the object's kinetic energy. The word net in here is quite important. Not so much so in this class, but very important in the future nonetheless. So we won't be talking much about net forces versus individual forces, because in our cases, the net force will be determined by an individual force, and all the other forces will be balanced. So here is the equation that we've just sort of described. Work is equal to, I'm going to write a delta there, change in EK. Remember, delta means change in. So, might be pretty obvious, but I'll label it as I usually do anyway. This is work done by the net force, but I'm just going to write work. And this is change in kinetic energy. So at its core, it looks like a really easy equation, but there's so much that we can do with it that it gets pretty complicated. We can expand each of these things out into multiple pieces. For example, you have to remember that work is also defined like this. Work is also F times S times cosine theta. So depending on what I'm given in the problem, I can write it in that form. I'll put a square around it even though we already have it. This one gets pretty crazy. Let's take it at face value. Change in always means final minus initial, so delta EK is equal to EF minus EO. Very often, one of those numbers will be 0, so keep an eye out for that. If your initial velocity is 0, this goes away. If your final velocity is 0, that goes away. Wait a minute, where am I getting velocity from? Well, you'll see that in the next line. Delta EK can also be written like this. EF would be the kinetic, well, that's EKF. Let me put that in there. EKF, EKO. Sorry about that. So it's delta EK equals EKF minus EKO. EKF would be expanded out like this. 1/2 mvf squared, and the counterpart would be 1/2 mvo squared. Another way to write delta EK, and I can combine that with this one, or I can combine the work with the top one here. So I could set this equal to this, or this equal to this. Finally, I'll put my last one, my favorite one. The change in kinetic energy can be found by factoring out the 1/2 and the m. As such, 1/2 m vf squared minus vo squared. My favorite because it is the shortest yet the most descriptive. Don't forget that close parentheses. All right, now don't let all that scare you. It'll be easy to choose them based on the context, and you can always just start here and start plugging in crazy stuff. The most general form would be to combine fs cosine theta equal to 1/2 m vf squared minus vo squared. I guess that would be the most detailed, using all the letters. Okay. Here's our first example. It'll be about half a page, so if you filled up most of yours, you might want to go on to the next. Okay. The prompt says, calculate final speed of a space probe. We'll say final velocity, just to keep things consistent. Calculate final velocity of the space probe. I'll also write the mass of the space probe right here. It'll be 474, I think. Yes, 474. To use my space efficiently, I'm going to draw the picture here, and I'm going to solve on the right-hand side of the page. So here's the info. The space probe begins moving to the right with a velocity of 275 metros por segundo. It is accelerating due to a very small force. If you've got a space probe out in the middle of nowhere, you don't need that much force to get it going because there is no air resistance at all. So it requires very little fuel. It'll be interesting to see how much faster this thing goes with such little force. How little? Less than 1 Newton. All along this distance, the space probe is going to experience a force of 0.056 newtons. That is way less than a pound. Way less than 5% of a pound. It's almost nothing. A breath of air. But if you accumulate this small amount of force for a long distance, you're going to do quite a bit of work on it. The distance will be 2.42 times 10 to the 9th. If you've got beef with scientific notation, just write 242 and then 7 zeros after it. So that's the distance. That is S. And the red one is F. Just so I don't forget, I'm going to label the green one as S. S is displacement in this case. We're trying to calculate final velocity using the work energy theorem. I don't believe I've missed any info. No, we're good. So let's start with the work energy theorem. The work done on this space probe is equivalent to the change in kinetic energy of the space probe. We want to introduce final velocity in some way. I'd say the best version of it would be right here. It's tried and true in my opinion, but You could also use this setup, 1/2 mvf squared minus 1/2 mvo squared. And I can already see that we're going to need to replace work also. They didn't give me a number for W, but they did give me F and S, so we'll put those in also. So let's see if we can, I don't want to take up too much space on the page. Here we go. Fs cosine theta equals 1/2 m vf squared minus vo squared. Okay, now we have to solve for final velocity. Can't work inside the parentheses yet. First thing would be to multiply both sides by 2, divide both sides by m. Or you can think of it like this. Multiply both sides by 2 over m. And over on the right, these two m's will cancel, the two 2's will cancel, and we're only left with vf squared minus vo squared. So we're already pretty close. I'm going to use 2 lines to write this. 2fs cosine theta over m equals vf squared minus vo squared. And from there, only 2 steps to get vf by itself. We add vo squared to both sides, and then we square root both sides. So if you don't feel strong with the algebra, you might want to do both of those steps by hand, one at a time. Add vo squared to both sides, then square root both sides. You should end up with this. This algebra is not as I would not consider this typical. I think this is pretty advanced, so don't let the algebra scare you on this problem. It's a little out of control, man. And now we have everything we need to know. Plug in our numbers. Even taking that even further, like the scientific notation makes it a little crazy. Tends to happen when you're talking about extremes, like extreme conditions like space. And that's why astrophysics is so tough. Because it's stuff like this. What am I looking at? Oh, cosine of 0. It's a 0-degree angle because F and S point in the same direction. Where am I getting 474? That's the mass, 474. So our final answer is $805. Give it a couple tries in your calculator, but like I said, this is pretty advanced with the scientific notation. I'm not putting this question on quizzes or anything. Should get 805, 804.6. What I'd like you to walk away from this problem with is the ability to, this is a good thing to memorize. It's only a couple letters. But I think what I want you to know is that you can replace work with Fs cosine theta, and that with delta Ek, you've got a couple choices. The bottom 2 are more descriptive. They're more applicable to different situations. Okay. One more example for the work energy theorem. Remember the point of the day. The work done on an object causes a change in energy. In order to change the energy of something, you need to do work on it. And sometimes that energy will change into potential or other kinds of form. Work is a change in energy. Work is a change in energy. Work is a change in energy. Here we go. Trying to keep this one brief. Calculate the height from which a gymnast falls if they reach the ground with a velocity of 8.4 meters per second. Now, if you're familiar with the conservation of energy, you could use the conservation of energy for this, but we're going to use the work energy theorem because that's the point of the lesson today. So here's the scenario. They start up top, maybe they jumped up here to begin with, and then they descend starting from a 0 velocity. They're going to fall down an unknown distance, which in the work energy theorem, the distance that they fall, the height that they fall from, is displacement, S. What force is causing them to move down? Well, it's gravity, of course. Gravity is our downward force, represented by mg. And that's all the information you actually need to solve the problem. Work is a change in kinetic energy. I don't have a number for work, but I've got all this stuff about F and S, so I'm going to plug in the Fs information. Fs cosine theta. Not sure which one to use, so I'll go one at a time. Like I've got all, where's my notes? Delta EK, I can write it in 3 different ways as we've just written. I don't know which one to choose, so I'll start here, see if it brings me anywhere. If it doesn't, I'll go here. If that doesn't work, I'll go there. So here it is, EKF minus EKO. Which of those is 0? It's going to be EKO. The starting kinetic energy of this person is 0 because they're dropped from rest. The distance that they go starts with a velocity of 0. That's nice, but I still don't have enough info to solve it. I also don't have F, so I'm going to plug in, I'm going to do 2 things. We'll replace that with 1/2 mv squared, and we'll replace this with mg. I'm doing too much at once. Let's leave that for another step. We're supposed to calculate, we don't have any information about kinetic energy, but hey, we've got that final velocity, 8.4, so I'll rewrite this with the velocity version. I'm not quite there. I don't have F, so let's see what happens when I replace it with mg. And that is actually the step that solves everything for us. Have a look at this. The m's cancel out. And now we have numbers for everything. Cosine is going to be, cosine of 0 Well, I'm missing a negative sign somewhere. It won't matter much though. So cosine is going to be cosine of 0, so that's going to be 1. G is 9.8, and VF is a value that we know as well. So we're dividing both sides by G cosine theta. I'll show this red step, this optional red step. I'm trying to go fast to not burn so much time. So I'll plug the numbers in from here. What we have left is S equals 1/2 VF squared over G cosine theta. For the sake of time, I'm going to cut it here. So it'd be 8.4 would go in for VF, G is 9.8, and theta is 0. You should get 3.6. But the main idea here is this idea that work causes a change in energy. That's the number one thing to remember, because after we practice this, after we practice a few of these problems, we won't use this concept very much, this algebraic concept, but this right here, work causing a change in energy, is going to be huge. That was pretty quick. If you have questions, do not hesitate to ask, but if you're all good, go ahead and post on Google Classroom. I'll talk to y'all soon.